In this video, we're going to implement a simple DeepONet in JAX to learn the 1D antiderivative operator. For this, we will first go over the theory of deep operator networks. Then we're going to download a very simple dataset, which we're going to inspect. Then we're going to implement the DeepONet architecture using the Equinox deep learning framework. Afterwards, we're going to train it in a very simple feed-forward supervised learning setting. And finally, we will assess its performance on the test dataset. Let's get started. The channel sponsor Pasteur Labs is currently hiring SciML and software engineering positions. Check out pasteurlabs.ai/careers for more details. Hi and welcome to this new video in the series on neural operator learning. This time we will look at the deep operator network, the DeepONet. A neural operator is a deep architecture that is designed to learn a nonlinear operator. This can be a lot of things, but typically we are interested in learning solutions to a family of parametric PDEs. In the more general case, neural operators can be mappings, for instance, from initial conditions of PDEs to solution fields at later point in time. For instance, think about the heat equation. If you have a heat equation and change the initial temperature profile over your domain, this will of course affect the temperature profile at a later point in time. And a neural operator would be a mapping between these two states, and so you can query it at a new initial temperature distribution. But they can also be used to map from parametric fields. So for instance, if you have a space-dependent diffusion coefficient on your heat equation and fix the initial condition, then of course, depending on how diffuse the domain is at a certain point, this will affect the solution field at a later point in time. So you can also have a mapping between those. So they are very general. So here for the DeepONet, we have a special case of a neural operator in that the DeepONet does not return the full output field, so it does not give you the full temperature field at the later point in time, but rather it takes as an additional input a query coordinate, so that you give it the entire input field together with the query coordinate, and then it returns the solution field, so the output field, evaluated at that query coordinate. And this is the more general case, for instance, when it comes to learning solutions to PDEs. Here for this tutorial, we want to look at a very simple introductory case of learning the antiderivative operator. So we want to have the neural network or the DeepONet become an integral solver. And we can frame that problem by an ordinary differential equation in that we say the output solution field, so let's call it V, is given in terms of its derivative. So we say the derivative of V is U. U shall be the input field. And additionally, we add the constraint that V at space index 0 shall be 0. And this is to remove the constant of integration. So the goal of the deep operator network is that we give it the entire input field U together with a coordinate at which we want to evaluate V, let's say for instance at 0.2, and then the DeepONet returns the value of V at that query coordinate. In more concrete terms, we will be working on a domain that goes from 0 to 1, let's call it omega, and we will divide it into 100 degrees of freedom, so spatial discretization points. And at these 100 points, we will evaluate U. So the input to the DeepONet is not the full continuous function, but the function evaluated at 100 points. So it will be a 100-dimensional vector. And then we also provide it with the query coordinate, which we set to a 1-dimensional vector. Then we return the evaluated value at the query coordinate. So in a mathematical term, we can write this as a mapping from an m-dimensional space. So this is the input we give in terms of the U field cross a 1-dimensional space, which will be the query coordinate, mapping to a scalar value, which is the value of V at that coordinate. So this is the more general function notation or mapping notation we could use for that kind of task. For a DeepONet, we now have typically the following architecture, in that here we will use the so-called unstacked DeepONet in the terminology of DeepXDE and the deep operator net paper, in that the input from the input field, so which is discretized at these m points, is going into something that they call a branch net. So this is a potentially complicated neural architecture, but importantly is just its signature. So it takes this 100-dimensional input field, so this 100-dimensional vector, and then maps it to a latent representation that they call the B vector, which is p-dimensional. In our particular case, we will set p to 40. So this is a mapping from a 100-dimensional space to a 40-dimensional space. And for this, we will use a multi-layer perceptron, an MLP, but of course, other architectures are also possible. Then we have the query coordinate that they denote by y, which enters the trunk net, which is also a neural architecture mapping to another latent representation they call the T vector, which has the same number of dimensions as the B vector, so it's also p-dimensional, in our case 40-dimensional. And then in order to get the result of the DeepONet, we will perform the inner product of these two latent vectors, so the B vector and the T vector, and then essentially we get this construct. So this basically means G, operator G, applied to function U, gives us function V, and then we have another set of brackets which is evaluate that function at y, so the query coordinate. So as mentioned, this also makes the DeepONet a bit different from other neural operators, for instance the Fourier neural operator. In case you're interested, I also have a video linked up here on an implementation in JAX. But for the FNO, the result of applying the operator is the entire solution field. And importantly, it is the entire solution field evaluated at the same coordinates as the input field is evaluated at. But for the DeepONet, the query coordinate can differ from these discretization coordinates we used for the input to the branch net. However, and this will be for the video here because of simplicity, if we use a dataset for training where the trunk coordinates coincide with the coordinates the branch input is evaluated at, we call this an aligned dataset, or the DeepONet DeepXDE terminology is an aligned dataset, and this is what we will be using for training. I have a couple more JAX-related notes, because when you see implementations of DeepONets in other frameworks like PyTorch or TensorFlow, they often do not directly follow this mathematical notation, because of course with deep learning you take into account that you can evaluate the DeepONet at multiple batches or at multiple samples. This could, for instance, mean you evaluate it at multiple input fields at the same time or multiple query points at the same time. But here I think the big advantage of JAX, and in particular the Equinox deep learning framework, comes into play in that by default all networks are single batch. And then we can get multiple evaluation formats just by using the automatic vectorization that JAX provides. And I think this is an extreme benefit. Let me highlight this. So you could be, for instance, interested in having multiple query points, because right now we only have one query point, but you could, for instance, say, well, I want to get the full field similar to what the FNO does, so I just evaluate my DeepONet at multiple coordinates at the same time. And this can be done by changing the mapping format from something where you have a one-dimensional query coordinate to a Q by one-dimensional matrix input. So basically a column vector in that sense, which has Q, and Q means the number of query points. And then, of course, the return shall be a Q-dimensional vector, because you want to have the output evaluated at all the query coordinates. So think again about the heat equation example, then you will have the temperature evaluated at all the query coordinates. And we can do this by using the automatic vectorization from JAX, which is jax.vmap, and then we place in here the neural architecture. We will see this in a second. And then within axes, we can say that we want to vectorize over the second input. So none means do not vectorize, and 0 means vectorize over the 0th axis. But for us, importantly, it means vectorize over that input. So we will vectorize over the query input. Another potential evaluation format is that we have multiple batches. So meaning that we get multiple input fields, but always have the one same query coordinate. And I see this should be raised to 1, but I think you get the point. So we now have an input, which is a matrix, and we have it n by m dimensional. So n means the number of samples, and m means the number of discretization points. So before that, we had that being 100. And then, of course, the return shall be n-dimensional vector, because we want to have the temperature value at the one query coordinate, let's say 0.3, for all the 100 fields we give to the DeepONet. And here for this, we will do in axes 0 and none. For the most general case, which is probably also the one you unfortunately have to implement in PyTorch or TensorFlow, and I think this, of course, once you have more axes than you would need for a single evaluation, it makes understanding the concept a bit harder. But here, of course, we just get that for free. So here for this, we have to do a nested vmap. So in the inner vmap, we do the mapping that we had before with none and 0 to vectorize over the query coordinates. And then in the outer vmap, we vectorize over the number of samples. And as such, we then get a mapping where the first input is an n by m dimensional matrix. The second input is a q by 1 dimensional matrix. And then we return an n by q dimensional matrix. So all the n different fields evaluated at all the q training points. And this is also the format we will be using during training, because we have that data set available in that format. Then a couple more notes on the training part. We will also see that in detail in a second. So here for that, we will use a dataset which exactly maps that format, and to make the training even simpler, we will use full batch training. So we will train on the entire dataset at once during one epoch. So no stochastic mini batching, but the rest of it will be very classical deep learning. Then let's get started with the actual coding. So we will go down and remove this hello world statement and start with the imports. So we will be using JAX. Then we will need jax.numpy, so jax.numpy as JNP. Then we will import jax.random as JR. Then we will import Equinox as EQX. So Equinox is this deep learning framework I mentioned. I also used it in a lot of prior videos. I like it a lot, and I hope I can also convince you that you look into that. Then we will need Optex. Optex is a gradient processing library in JAX that it provides us with the Adam optimizer. Then we will use matplotlib.pyplot as PLT for visualization. And I will also import a very simple progress meter. So let's say from tqdm.autonotebook import tqdm. Then let's shift enter that cell. As a first step, I want to download the data set. For this, I will just copy paste the cell in here. This is the dataset that was also used in a tutorial on the DeepXDE library. We will download it from a GitHub repository that is associated with the course Deep Learning in Scientific Computing that is given at the ETH Zurich. It is a very small dataset. So training has 230 kilobytes and the test dataset has 1.5 megabytes. So it should be a fairly straightforward download. Then let's read in the dataset. So let's say dataset train is jnp.load, because it is given in terms of a compressed NumPy array, so we can just use JAX-NumPy to load that into memory, and then provide it with the name. So it's called antiderivative aligned train. And recall, aligned meant that we have the trunk inputs at the same coordinates as we have the branch inputs evaluated. Then we need to set the keyword command allow pickle equals true to correctly load that. And then this can be indexed as a dictionary to get our inputs. So let's first start with the branch inputs and then give it the suffix train and say this is dataset train indexed at capital X. And then we will index it at 0 here, because the X or the input to the model both contains the branch and the trunk inputs, but for the implementation here, I want to keep them separate. So actually this returns a tuple, and so we will just index that tuple at the 0th index, which gives us the branch inputs. Then we will do the trunk inputs train are dataset train indexed at capital X again, but this time with 1. And then we will have the outputs for training So these are the evaluated antiderivative at the trunk inputs. And this will be dataset train indexed at lowercase y. All of these three training components are NumPy or JAX NumPy arrays. So let's look at their shape. So let's say branch inputs train.shape, trunk inputs train.shape, and outputs train.shape. Then we get these three shape tuples, and we see all of them have rank 2. So there are 2 ranks or 2 axes here. For the branch inputs, we have a 150 by 100. If you recall, this 100 is referring to the number of discretization points, and then 150 means that we have 150 samples. So basically we have 150 functions for which we want to know the antiderivative. Then we have the trunk inputs. So we know we have a one-dimensional query coordinate, so this is a 1 here. But then we have 100 because we have 100 different query coordinates. And now the concept of the aligned data set comes into play, that this 100 matches that 100. So that is because we have this aligned data set. And then the shape of the output is 150 by 100. So this is essentially what we also saw earlier with the clever nested vmapping, in that we get an output evaluated for all the 150 samples at all the 100 query coordinates that we have available. So these 100 badges of one-dimensional query coordinates. Then let's do something similar for the test dataset. So let's say dataset test is jnp.load on the antiderivative operator test, and then also do the allow pickle equals true. Then let me just copy in basically an adapted version of that, and then we can also inspect the shape of the test. So let's look at it and compare it with the training. So now we have a 1000 by 100 for the branch inputs in the test data set. So this means for the testing we actually have more samples, but they are of the same kind. So they are also 100-dimensional branch inputs, and we also have a 100 different query coordinates. And this actually also has to be the same. So once we have a DeepONet trained, or at least the way we're going to implement it here, this 100 has to be fixed. It then always requires us to have this 100-dimensional branch input. Okay, but let's visualize the dataset to get a feeling of what it looks like. So let's start with the train dataset. And again, this remark, we have this aligned dataset, which means that the trunk inputs actually are a grid on which the branch input was discretized. Let's also take a quick look at it with trunk inputs train. So we see that it is an 2-rank array, so we have like 2 sets of braces here, and then we see that it is essentially what you would get if you do numpy.linspace. So it's linearly spaced from 0 to 1 with 100 entries. So we can use this as the grid for plotting. Let me note that down in a small comment and say due to the data set being aligned, sorry, this was not spelled correctly, we can use the trunk inputs as a grid. So let's do the plotting and say plt.plot. So this first visualizing the branch inputs. So let's say trunk inputs train. So this will be our grid. So how do we have to index it? So we will do all the query coordinates and then do a 0 here in order to get rid of that singleton dimension. Then let's do branch inputs train indexed at 0 and colon. So 0 now means we want to visualize the 0th entry in the train dataset, so the 0th sample function. And then colon means we want to, of course, visualize all the 100 points we have available. Let's attach the label and say that is the input. And in the same plot, let's also plot the output. So trunk inputs train colon 0, and then outputs train indexed at 0 colon, and attach the label being the antiderivative. Let's add the legend and add a grid, and then let's execute that. So here we see these two functions. In blue we have the input and in orange we have the antiderivative. So the blue function, let's take a look at it. So here we have the 0 value, so it is constantly negative. And the antiderivative, you can now think of it in that the blue function has to be the derivative of the orange function. And as you see, the orange function has a negative slope, and as such it makes sense that the blue function in the entire negative regime. Of course, we see some sort of like shape in the blue function, which is barely visible because the orange function almost looks like a straight line. Maybe if we plot a different sample, let's switch to the second sample, and I think there it is more nicely visible. So the orange function is the function actually that we want to have as the output of the DeepONet, but for a second think of it as the function we want to derive. And here we see its slope is constantly positive, but there is definitely a point where the slope is smaller than it was in the beginning. And this is also noticeable here in the blue curve, in that it is always in the positive regime, and in the beginning it goes down because also the slope decreases, and then there is a point where there's almost no slope, so it is very close to 0, but then it goes back up. And so you now see that the data set consists of these two functions, and the DeepONet shall now be a mapping that if we give it the entire blue function together with one query coordinate, let's say 0.2, the task of the DeepONet is to evaluate the orange function. And this would then be, well, giving the query coordinate 0.2, it will likely give us a value around 0.2. Then let's start with the implementation of the architecture. So let's go to the next cell and then define a class and call it the DeepONet1D. And this shall subclass from Equinox.module because we will use Equinox as our deep learning framework. Then we have to define the attributes. So for this we will have a branch net, and this branch net shall be an Equinox MLP. So Equinox has a built-in architecture for multi-layer perceptrons. So let's say this is equinox.nn.mlp. And then we will have a trunk net, which is equinox.nn.mlp. And finally, one thing I did not tell you earlier, when we do the inner product, after we have produced our two latent vectors, we will also add a bias, and this will just be a JAX array. And then next up, let's scroll down a bit and then define the constructor. So def_init, and first is getSelf. Then we have to define the in size for the branch net. And this refers to how many dimensions we have our input function discretized at. So for our example, this of course will be 100, but I just want to give this here as a free argument. Then we have to define the width size. So this is an argument in order to denote the width of the MLPs. And for simplicity, we will use the same architecture for both the branch and the trunk net. So this both refers to the MLP width size of the branch and the trunk net. Then we have the depth that refers to how many hidden layers there will be in the MLP. And then we have the interact size. That's at least how I want to call it here. The size of the latent dimension of these two vectors that we have to produce. And then we also need an activation function. And then ultimately, as a keyword-based argument, we will hand over the key. So this is a JAX pseudorandom number key, and that's a very typical pattern you see in Equinox, having this as the keyword argument, because we always need a random key for the reproducible pseudorandomness we have in JAX. And then let me note as a docstring, just to have that also written down, that for simplicity, branch and trunk MLP are configured similarly. Of course, you can do all kind of fancy things with DeepONets. You can also introduce convolutional architectures for the branch net, but here this is just the easiest example we can implement. Okay, then in the constructor, we can instantiate branch, trunk, and bias. So for this, we first have to split our random key into two separate keys for the branch and the trunk net. So let's say B key and T key is jr.split on the key, and then self.branchnet is equinox.neuronetwork.mlp, And then this MLP first requires us to define the insize, and for this we will set it to insize branch, because this is the branch net, so this will be the input size, a 100-dimensional vector. Then the output size shall be the interact size, because the branch MLP maps to this latent dimension. Then we have the width size, which will be the width size we had also as an argument to the constructor. And then we have the depth, which is the depth we also had. We will set the activation to the activation. And then finally, we will set the key to the branch key. Then we can instantiate the trunknet. So self.trunknet is equinox.neuronetwork.mlp. And here as an insize, and now this is crucial, this takes 1, because we want to restrict ourselves here to one-dimensional problems, so where we have a one-dimensional domain on which the field is defined. So this is x, and for this we have a one-dimensional coordinate. And this is also reflected by calling this the DeepONet 1D. So if you had 2 spatial dimensions, you will set this to 2. If you, for instance, had 2 spatial dimensions and a time dimension, you can set it to 3. But now importantly, the Equinox MLP either wants us to set the insize to an integer or to the literal scalar. And this is actually a difference, because 1 means that it is a structured input, so it's definitely a vector with shape 1. Whereas for a scalar, it would just be a float. And in order to map the signature of being a mapping of m cross 1 to r, we actually have to set this to 1. If we set this to scalar, that would be a mapping of rm cross r to r. I mean, mathematically, there might not be that big of a difference, but actually this is very important because it also affects how the automatic vectorization with JAX works. Okay, let's go down. So we have the insize set to 1. The outsize is of course the interact size, because that also produces a latent dimensional vector. Then we have the width size being the width size. We will set the depth to the depth. We will set the activation to the activation. And then we have the key being the trunk key. Now there is one more thing that we have to consider here, and that is the trunknet also gets a final activation. So because by default MLPs do not have an activation in their final layer, that kind of makes sense, because activations are squashing the order of magnitude of these neurons. And when we have a final layer, we want to have this a bit more flexibility in the order of magnitude. So this is usually not activated. You also see that if you hover over the docstring and then see it has the argument final activation, and it says defaults to the identity, so no activation. But for the trunknet, we actually want a final activation, so we will also set the final activation to the activation function. And then ultimately, let's also add the bias, and this one will be initialized as a 0 one-dimensional vector, so jnp.zeros on a one-dimensional vector. Okay. Then let's get to the forward method, or the call signature, and this shall take self as well as x branch and x trunk. And here this deviates a bit from how you would typically implement these DeepONets in PyTorch or TensorFlow. So here we will have those as 2 separate inputs. And this also later on then helps us with the automatic vectorization, because as you saw in the intro, we can then either vectorize over the trunk inputs, over the branch inputs, or nestedly over both. Let me also write down in the docstring the expected shapes of them. And this expected shape refers to an unmodified version. So when we have not used the automatic vectorization yet. So x branch dot shape should be insize branch, comma, so in our case a 100-dimensional vector, and x trunk dot shape shall be 1, and then return shape, and now this is important, is scalar. So this is what I meant earlier. So the return shall not be any dimensional, so it should just be a float value. So let's do that. And the first step in our call method is that we say branch output, or the branch component in this latent dimensional space, is self.branch branchNet applied to X branch. And then we have trunk out being self.trunkNet applied to X trunk. Then we will perform the inner product. So the inner product between these two is jnp.sum of branch out multiplied with trunk out. But now importantly, usually when you do the sum command with numpy, this also reduces all the axes and you will get back a scalar. And in order to prevent this, I will use keepDims equals true. So then it actually returns a one-dimensional vector. So it will kind of produce an inner product of two 40-dimensional vector, because we will set that latent shape to 40. And then it produces, as a result of that operation, a one-dimensional vector. And this is also helpful because the bias is a one-dimensional vector. And then we can essentially say that this function shall return inner product plus self.bias, but now importantly indexed at 0. And this sounds a bit strange, but with indexing at 0 here, we remove the shape, or we remove the structure and actually get this scalar shape that we desire. So let's shift enter that cell to register our architecture. Okay, then let's use the architecture and instantiate it just as a test case. So let's call this antiderivative operator, just be really brave about what the DeepONet shall become ultimately. And then let's say this is the DeepONet 1D and set the insize branch, so insize branch to 100. Set the width size to 40, set the depth to 1, set the interact size to 40, and set the activation to JAX neural network.relu. And then of course we need to provide a key. So let's use JR for JAX-random and then say pseudo-random number key 0. So I just arbitrarily chose the width size to be 40 and just have one hidden layer. So this follows the tutorial on the DeepXDE library. Of course, feel free to play around with the parameters. Here we have a very simple problem. So the MLPs do not have to be too capable, but of course you can potentially improve the performance by increasing the capability of the embedded network. Let's shift enter that, and then let's just print out it and see that it actually gives us a representation here. This is very common for the Equinox deep learning framework. So I would just switch to this crawlable element, and basically you see this is a structure which has as a branchNet an MLP consisting of two linear layers and an activation function. It has a trunkNet with an MLP, two linear layers and an activation function, and then ultimately at the bottom we have a bias which is a float 32 array with shape 1. Okay, let's remove that cell because I don't think we need to print it anymore. And then let's implement the training loop, because of course in the beginning the parameters are initialized. The DeepONet will likely produce garbage as a result. So let's train it. For this we will instantiate an optimizer. This will be the optex.adam optimizer, and we will give it a learning rate of 1e minus 3. And then we can instantiate an optimization state, because of course Adam is a stateful optimizer. It keeps track of a momentum. So we will say optimizer.init, and then we have to provide the parameter space or the parameter object which shall be optimized. And for this we have to filter our architecture by using equinox.filter on the antiderivative operator with the filtering rule equinox.isArray. If that sounds a bit strange to you, I would highly recommend to check out the video I have linked up here on a more easy task using Equinox to just learn the sign function, where I go over more detail on why we do the things we do. But for now, this just means that we extract all the parameters. So these are the weights and biases in the linear layers, and also the bias vector we have at the very end, and then concatenate them or consider them as one big parameter vector. Okay, then for each training we need a loss function. So let's define a loss function, and this shall take a model. So model shall represent the DeepONet at a certain stage within the optimization, and then in order to compute a loss, we need to make a prediction with the network. And let me also add the highlight that this shall be a full batch training. So that's also the reason the loss function does not take the current batch subset of the training data, because it will just capture the entire training data from the environment. So in order to make a prediction, we now will be using the automatic vectorization I mentioned earlier, and we will use it in the last format, where we actually have two nested vmap operations in order to get the signature, which can both consider more than just one sample and more than just one query point. So let's call this the predictions and say that the predictions are jax.vmap on jax.vmap on the model, with the inner vmap taking indexes of none and 0 to vectorize over the first or second, depending on how you count, from 0 to 1 entry. So in other words, we vectorize over the trunks, but don't vectorize over the branches. And then the outer vmap shall vectorize over the branches, but not over the trunks. And then we will just apply that function to the branch input strain and the trunk input strain. And those two arrays this function captures from the environment. Let me also note that down, that essentially here we vectorize over both the batches, or you might call it also samples, and the query points. Then we can use the predictions to just compute a mean squared error and say jnp.mean on jnp.square on predictions minus outputs train. And then this function just returns the mean squared error. With a loss function, we can then define an update function. And as said, if you're not very familiar with how to train Equinox networks in JAX, this of course looks a bit strange. Conceptually, of course, the same thing happens as what you would do with Keras or TensorFlow or PyTorch, but of course it's expressed in a bit different way. So let's define an update function. This shall take the model and a state. So state means an optimizer state. And then an update function will first differentiate or compute the derivative of the loss. So for this, we will say that loss and gradient is equinox.filter value and cred applied to the loss function on the model. So also a quick detour in case you're not too familiar here, but automatic differentiation in JAX is implemented as function transformation. A very similar function transformation you have with vmap. So vmap transforms or changes the signature of the model to take more than just the number of axes it was actually defined to take. But with the automatic differentiation, it changes the signature, because the signature of the loss function is that it takes a model and returns a loss. And now this changes in a way that it returns the loss, as it happens if you would apply the function to the model, but also returns the gradient. This gradient we can then use to feed the Adam optimizer. So we will say that updates, new state is optimizer. It captures from the environment dot update on cred, state, and model. And then this gives us updates. So basically these are updates to the parameters of our model. And then we say new model is equinox.apply updates on the model and the updates. And then ultimately the update function shall return the new model, the new state, and the loss. And then typically, since the update step is the most computationally demanding step in the training loop, we will use the just-in-time compilation of JAX to improve its runtime. And here for that, we will use the filtered version from Equinox and say equinox.filter JIT. Then we can implement a training loop. For this, I also want to record the loss history. So this will just be an empty list for now, and then say for underscore in TQDM to create a progress meter of range of 10,000, because I want to do 10,000 epochs or 10,000 training steps also in that sense, because we do full batch training. So this is more than sufficient to learn this antiderivative operator. And then in each iteration of the training loop, it says that antiderivative operator, comma opt state, comma loss is update function applied to antiderivative operator, comma opt state. So take the current state of the model, take the current state of the optimizer, produce a next state of the model, produce a next state of the optimizer, and for inspection also give us the current training loss. And then we can say loss history dot append loss. And now if we execute that cell, you see that the TQDM progress meter pops up and a training commences. Okay, here we go. The model is trained on my laptop CPU. That took around 1 minute and 40 seconds, so it's not a strong CPU. Likely if you do that on a GPU, it will be 10-20 seconds. Then let's plot the loss history and say plot.semilog y on the loss history, and then see how our training proceeded. And let's see. So here we go. Initially, we started at a loss that is, let's say, around 10 to the 0, so it's a little bit below 0.8 maybe. And then we have an initial transient phase going down to 10 to the minus 4, so decreasing by about 4 orders of magnitude. And then we have this slow fade-out convergence, where we also see these oscillatory behavior. So this is a very typical phenomenon you see here. Of course, for that sense, it would be reasonable to maybe introduce a learning rate scheduling to reduce these oscillations. But I think for this very simple tutorial, that is more than fine. With our network now being trained, we can evaluate it. So for this, I want to plot its prediction on the test dataset. So let's do a very similar plotting to what we had before. So remember, since the dataset is aligned, we can use the trunk inputs as a grid for plotting. So let's say plt.plot on trunk, or maybe let's go to the next line and say trunk inputs test. And then we had to index that at colon and 0. And then the next was the branch inputs. So let's do branch inputs test at 0 colon. So let's first start with the first test or 0th test sample, and then attach the label and say that this is the input. Then next to it, let's plot the reference. So this is the true antiderivative, trunk inputs test on colon 0 together with outputs test at 0 colon, and then attach the label true or ground truth. Let's maybe just call it GT antiderivative. And then let's also plot the prediction. So plt.plot on trunk inputs test colon 0. And now we have to query the model. So let's go up and back to the intro. So where we saw that by default, we just have that version of the DeepONet, which of course would not help us to make a full field prediction. So now we will use the 0, depending on how you count indexing, but that version of doing vmapping by vmapping over multiple query coordinates. So let's go down here and they say JAX.vmap on antiderivative operator, and then say in axis, it did not pop up. So in axis being non, 0 to map over the query coordinates. And then as inputs, we will use the branch inputs test, but we also want to be at the 0th sample and then colon. So because we did not vmap over multiple inputs, so we have to at least select one. And of course, it makes sense to select the same as we also use for the others, because otherwise, what are we comparing ourselves against? But we will use the full trunk inputs. Then let's also attach a label to this plot and say that it is the prediction, or more precisely, it is the vmap prediction. So it's not just querying the model once, but at multiple inputs at the same time. But of course, it will use the same trained weights for this prediction. Let's add the legend and also add the grid. And if we shift enter that, here we see that in blue we have again the input. So recall this is of course different because we are now in the test data set. And in orange we have the antiderivative, and the blue is supposed to be its derivative. and we see that this function has a positive slope, but of course there are regions where the slope is higher than the others. So the blue function is constantly in the positive, makes sense because we have a positive slope, but then there is this region here where it is the steepest, and then we also have the highest value in the derivative. But this is just the concept of what these two functions relate to each other. But now the point is that we have in green the prediction, and as you see it's very barely noticeable. Maybe let me open this separately here and zoom in, but you see that the mapping is very close. So the green is close to the orange curve. So here's a little bit off, but on other regimes, it's a very nice mapping. So it turns out that the DeepONet is very capable, at least for the particular dataset we look at, to learn this antiderivative mapping. Let me close that. Of course, you're free to play around, so you can change the samples. So for instance, go to the first sample, but be aware that you have to adapt it here, here, and also here. Of course, this is just a qualitative comparison. We are also interested in a numeric value that shows us how good it is. But for this, we will do a prediction on the entire test data set. So let's say predictions test is JAX.vmap. And now we have to use again the nested vmap. So we will use another vmap and then say antiderivative operator on in-axis being none and 0, and then the other vmapping. Sorry that the screen recording is so laggy. I think my laptop is a little bit getting to the limits here with the recording running next to it. I hope it's still nice to follow. So the outer vmapping shall be 0 and none. And then once the function transformation is done, this is also the reason we use another set of braces, because that just transforms the antiderivative operator's evaluation. But then of course we also have to perform the evaluation itself. So let's call it on branch inputs test and trunk inputs test. So now we have a bunch of predictions. So if we look at the shape of the predictions, so we see they are 1000 by 100. So also what we had in the test data set of before. And now our task is to compute a metric. And there are a lot of metrics one can compute here, but I believe the most reasonable metric to do is the mean normalized L2 error. By that we compare compute an L2 error over all the 100 points separately for all the 1000 samples and normalize it with respect to the reference and then compute the mean. So this will be a bit tricky, but I hope you can follow me. So let's first implement a single batch version, which I want to call the normalized L2 error. And it shall take a prediction and a reference. And those are supposedly 100-dimensional vectors both. So for this, we will first compute the difference norm by jnp.linalg.norm on prediction minus reference. And then let's also compute the reference norm, which is jnp.linalg.norm on the reference. And then this function shall return difference norm divided by reference norm. So this is a normalized L2 error. It's normalized because we divide by the norm of the reference. Now we again use one of JAX magic with automatic vectorization in that we vmap that function over all the predictions and over all the references. So we will do JAX.vmap of the normalized L2 error. And now we don't have to provide an in-axis because by default it will vectorize over the 0th axis for all the inputs. We only did the in-axis here because there are inputs that we don't want to vectorize over. But if you're just fine with vectorizing over the 0th axis with all inputs, no additional keyword argument is needed. And then we can just call it on predictions test together with outputs test. So if we execute that, it gives us a big array. Let's just inspect the shape. We see it is 1000 dimensional. So it gives us a metric for all the 1000 samples we have in the test data. And then we can see, so there are values in here. So here's a 0.005, 003. So these are significantly low value. We also have some that are a bit higher. We are interested in the mean over that data set. Let's compute the mean. So let's say mean test, or maybe let's do it differently and call it the test errors. And then we can compute the mean test error by saying that this is jnp.mean of the test errors. And let's also compute the standard deviation over the test error, saying jnp.std over the test errors, and then just providing or printing that out. We see that our mean test error is a 0.010. So that's a quite low value. So it's 1 times 10 to the minus 2. That's a good value for those kind of scenarios, for these normalized errors. So being in the range of 10 to the minus 2 to 10 to the minus 3 is something that kind of represents a good fit. Standard deviation is a bit high, so we do have a lot of samples that actually are different from that mean. But of course, this is for more sophisticated investigation of the architecture. We at least can be sure that we learn something meaningful. So there's definitely an improvement, or definitely something that the DeepONet does. This channel is supported by Pasteur Labs and the Institute for Simulation Intelligence. Click the link in the video description to find out more how they merge machine learning and simulation in order to reimagine the scientific method. Also, a big thanks to all my Patreons. If you also want to support my vision of free education on advanced mathematical topics, you find the link to the Patreon page down in the video description. I hope you enjoyed that video. If you did, then please leave a like and consider subscribing to the channel. There is more content on physics-informed machine learning, neural operators, and all these kind of topics, and I'm pretty sure you are interested in other videos as well. Here you will see some of them, and I hope to see you in one of the future videos.